Hi students. So let us study the time response of a system in this video. Before we proceed, so these are the few things you should be knowing: transfer function, poles and zeros, Laplace and Laplace inverse Laplace of certain functions, and you should know what is time response of a system. Okay, with these prerequisites, so let us move on to time response of a system. So let us consider a block diagram of a system. So and this is the input port, this is the output port. We want to see what is the response of the system, what is the output of the system with respect to time. So starting from t equal to 0. Now for that we have to apply the input. So inputs can be uh, it can be a impulse, it can be a impulse input, it can be a step input. It can be a step input. So these are the typical inputs. So along with this, we can also consider ramp and parabolic inputs. So this can be a impulse, unit impulse, and it can be a unit step input. This can be unit ramp, and this can be a unit parabolic. So now, how do we represent this? So this is represented by uh, delta function whose magnitude is equal to 1 for all values for values of t equal to 0, and its value is 0 for all values t other than 0. So this is an ideal impulse signal which will be represented by something like this. If this is t, if this is at 0, then you will going to have a magnitude of 1 only at t is equal to 0. The values, the output, the input itself is 0. When it comes to unit step input, so this you write it as u of t, and it is equal to 1 for all values of t greater than or equal to 0, and its value is 0 for all values less than for all values of t less than 0. Meaning, if this is your t and this is at t is equal to 0, then you'll end up with, if this is unit step input, it is of magnitude 1 for all values of t greater than 0 including 0, and it will be 0. You can just write it this way. This is this exactly going to this. And for ramp, so this is r of t will be equal to t for all values of t greater than 0, greater than or maybe greater than equal to 0. So something like this. So this is how, if it is t, then it is keep going like this. So this will be of unit magnitude. Slope is unit, and here it is. This can be t square by 2, where the response would be something like this. So this is t, and this is your r. So these are different inputs. So this is delta t, this is u of t, this is t, and this is t square by 2. These are all unit magnitudes. Of course, we know that we define the system by a transfer function. We define system by a transfer function. Of course, it can be open loop transfer function or a closed loop transfer function. We're going to define that in the form of poles and zeros. It can be s plus z1, s plus z2. It can be s power n. This is s plus p1, s plus p2. Of course, you can have any number of poles and zeros, and the denominator will, because we know that denominator will indicate the poles and the numerator will indicate the zeros of the transfer function, whether it is open loop or closed loop. Now we shall define two parameters. What is the order of a system? Order of a system. Order of a system is nothing but number of number of poles of a system. Of a system. System is nothing but order of the system. Now assume that you have a This is irrespective whether it is open loop transfer function or closed loop transfer function. So if I write a transfer function something like maybe assume that GFS into HFS, which is an open loop transfer function, if it is 10 by s into s plus 3. So then what is the order of the system? Order of the system is, because you have one pole here, second pole here, the order is 2. Suppose if you write CFS by RFS for the same, this will become 10 divided by s into s plus 3 plus 10. So what is the order of the system? Still order is 2. So order of the system doesn't change with open loop transfer function and closed loop transfer function. The number of poles in the denominator remains the same. Their positions are different, but the number remains the same. So that's why this is the order of the system. Then we define something like type of a system. Type of a system. So what is this type of a system? Now this type of a system is defined for, of course, by considering open loop transfer function only. So you're considering open loop transfer function only for defining type of a system. Then what is type of a system? It is nothing but how many number of open loop poles are there at the origin. Supposing that this is s into s plus 3. Where you're locating, this has to be GFS into HFS. If GFS into HFS is this, then it will have this and this. How many poles are there at the origin? How many open loop poles are there at the origin? It is 1. So it is type 1. It is type 1, but order 2. So type 1, order. Suppose if I write this 1 over s plus 6 is your GFS into HFS. You write the opposite representation. You can represent this as here. This is minus 6. Is there any pole at the origin? No. So this is type. This is type 0. This is type 0. Suppose assume that you have a transfer function GFS into HFS, which is nothing but 6 plus s into s square plus s minus or s minus 3. How do you represent the poles and zeros? So here you have two repeating poles, and here it is at plus 3 and you have it at minus 6. So what is the how many number of poles are there at the origin? Open loop poles. There are two open loop poles. So I can say the type of a system, the type number is 2. So this is a type 2 system. This is a type 2 system. So we have type 1. This is type 1. This is s power 0 like. So there are no zeros at the origin. Uh, there are no poles at the origin, and there are two poles at the origin. So it is type 2, type 1, type 0, type 0. So that's about type and system. So let us move on to the Laplace of the inputs. So we have considered these inputs: so impulse, step, and ramp and parabolic. So let me just take R of t as delta t, which is an impulse. Its RFS, its Laplace is 1. Its Laplace is 1. So let us take a step input. Let us take a step input, which is R of t is equal to U of t. Its RFS is 1 over s. 1 over s. So let us take a ramp input. Let us take a ramp input. The R of t is equal to t, then R of s, which is nothing but Laplace of this. It is 1 over s square. If I take a parabolic input, R of t is equal to t square by 2, then R of s is equal to 1 over s cube, 1 over h cube. This is what is Laplace of impulse, Laplace of a step, Laplace of a ramp input, Laplace of a parabolic. So we are writing the Laplace transform of the input, Laplace transform of the inputs. So let us consider, of course, let us just consider these two basic inputs for uh, different order of the system. So let us consider first order system. First order system and try to find its time response. Let us find its time response of the system. So let us consider a RC network, which is this. So this is V in, this is V naught, this is RC. This is a very well-known circuit. If you want to write V naught of S by V in of S, which is a transfer function, it will be given by 1 over 1 plus SRC. I can replace RC as, I can rewrite RC as tau because tau corresponds to time constant. I can rewrite this expression as 1 over 1 plus S tau. So now let us assume that R is equal to 1 kilo ohm and C is equal to 1 microfarad. So then this tau becomes 1 milli. 1 milli. So let me take a unit impulse input for this. So then what is V in of t? Then V in of t is equal to delta t. Then what is V in of s? V in of s is equal to 1. So that's what we know here. So this is what is for the impulse, the Laplace is 1. So V in of s is 1. So what is V naught of s? V naught of s is equal to V in of s divided by 1 plus s RC. So what is V in of s? It is 1 divided by 1 plus s is how much? Of course, this is s. This is tau. Correct? This is tau. So now we have V naught of s as equal to 1 over 1 plus s. Now what we are looking at is V naught of t. So how do you get V naught of t? V naught of t can be obtained by taking Laplace inverse of V naught of s. So V naught of t is nothing but Laplace inverse of V naught of s. So we know some of the Laplace inverses standard form, which is nothing but 1 over s plus a. What is Laplace inverse of 1 over s plus a? It is e power minus a, e power minus at. What I have? What I have is now 1 over 1 plus s tau. So this is what is V naught of s is now V naught of s. So I want to find V naught of t, which is nothing but Laplace inverse of so it is 1 over 1 plus s tau, but it is not in this form. So I have to bring it to this form. Let me take tau outside. It is a Laplace inverse of, when I take tau outside, it will become 1 over tau plus s, and this is 1. Right? So then this is what? 1 over tau by s plus 1 over tau. Uh, just give me a minute. So I just continue this in 2 minutes. Excuse me for that.